Right, let's look at an example. Here we have a pipe which is open at one end, and it is told that it has lowest harmonic frequency at 330 hertz. So technically this is the natural frequency of the pipe. Alright, we want to know what is its next resonant frequency. Alright, so for pipes with open end, we have already learned from lectures: one end open pipes. One end open pipes has the frequency relation. The progression of its resonant frequencies goes like N times V over 4L. N is the nth harmonic, V is the speed of the wave, and L is the length of the pipe. Okay. Therefore, the N for an open pipe will go as 1, 3, 5, and so on and so forth. Only odd harmonics exist for one and open pipes, right? What does the lowest harmonic look like, or the natural frequency look like, if we draw out a one end closed and one end open pipe? Well, with at the closed end there is no movement of air molecules, so there must be a node. The molecules don't move anywhere. And at open ends there must be antinode, because there is maximum movement of air molecules here, so maximum disturbance. So the wave is, the harmonic shape is like this. This is the first harmonic, for which n equal 1, and the frequency is the lowest. F1 is V over 4L, and that's given to us as 330 hertz. Okay. Now what is the next resonant frequency? The next resonant frequency will be for n equals 3, meaning what does it look like then? We can add another node in between, right? For the same pipe, at the closed end it must have a node, and at the open end it must have an antinode. In the middle we can just add a node, alright? So that the wave shape, the harmonic shape, it looks like this. Alright? So that at the open end we have an antinode, maximum displacement or maximum movement of air molecules, and at the closed end we have a node. This is what the third harmonic, or actually the second harmonic, for which n equals 3, whichever way you want to think of it, this is the next resonant frequency. There is nothing in between. The F2 doesn't exist. Alright? And we talked about that in our lecture. F3 is using this relation right here. It should be 3 times V over 4L. What is V over 4L? It's just F1. So whatever we have for F1 we multiply by 3 to get next resonant frequency. So 3 times 330 gives me 990 hertz. This is the next resonant frequency if the pipe is open at one end. Now what if pipe is open at both ends? Open at both ends. Then if we ask the same question for the same natural frequency, how does the answer change? Well, for open-ended pipes, our relation for frequency is the harmonic frequency progression goes like N times V over 2L. Alright, this is for all n equals 1, 2, 3, and so on. So it doesn't need to be odd numbers. It can be all positive numbers. Okay. Therefore, the lowest one is F1 as usual. This is our lowest or natural frequency, and this is V over 2L. This is given to us to be 330 hertz, right? And from there, what is the next harmonic frequency? The next should be F2, which is 2 times V over 2L. What is V over 2L? V over 2L is just F1. So if we multiply 2 with F1, we get 2 times 330 gives us the next resonant frequency, which is 660 hertz. Now let's this is how the answer changes. So we see that the next resonant frequency for open-ended pipes is smaller than for one and closed pipes. Now let's look at how the harmonics look for open-ended pipes. If both ends are open and the pipe looks like this, at both of its ends we must have antinodes because of maximum motion of the air molecules, right? So the wave, the first harmonic looks like this. Alright, this is basically half of a wave. Now what does the second harmonic look? We can include another node in between, keeping antinodes at both ends. So we have a shape like this, right? For antinodes at both ends, if we add another node, here we had one node, in this case we have two nodes, therefore we get a frequency of 660 Hertz. Right? That's the second frequency. Okay? So this is half a wave, this is one complete wave. Alright? This was 1/4 of a wave, and this is half a wave. Okay? Now let's look at what would happen if we choose the instrument to be a stringed instrument like a guitar or a piano. For strings, we have a situation like this. The first harmonic looks like there must be nodes at both ends, right? The first harmonic looks like this. The second harmonic would look like something like if we add another node in between. Okay, so this is the lowest, F1. This is the next harmonic. If we add another node here, the second one would look like this. Okay, so we see that this is half a wave and this is one full wave, similar to what we had for pipe at both ends open, where the first wave was half a wave, the first harmonic was half a wave, the second harmonic was one full wave. And it is not a coincidence, therefore, to note that our frequency progression for stringed instruments or waves, standing waves produced on strings between strings attached between two ends, like for a guitar or a piano, it's the same relation as open-ended pipes, NV over 2L. Therefore, F1 is V over 2L, which is 330 Hertz. Since the formula is the same, the next resonant frequency must be the same as the one for the both ends open pipe. Okay, so 2 times 330 is still 660 Hertz. Alright, so this is basically a demonstration of the differences and similarities between standing waves produced on different kind of musical instruments. Okay, I hope this makes sense. Thank you.